Okay, so in the last section, 2.7, we defined the derivative at a point, and now we're going to talk about the derivative as a function. So hopefully it's somewhat clear that the value that we get from, so what we saw last time was that, oh, yeah, the derivative at a point was equal to this limit, right? And so hopefully it's clear that if we were to change a, that this limit would possibly change. So it means that this function, whatever comes out of, or if we plug in a, the output, whatever that may be, depends on a. So this defines a function. So usually we denote, we use a for a constant and we use x for a variable. So I'm going to start writing as f prime of x. And so this is a function. And the variable is x. Okay. So what is the domain of this function? So since we have a function, we can always ask what the domain would be. And the answer is that there's one restriction that we have, and that is that we can't define the derivative at a point where f is undefined. Okay, because f of a shows up, or f of x, but we have to actually evaluate the function at the point where we're trying to define the derivative. So if f is undefined there, then we can't move forward with the definition. So we can't define the derivative anywhere that f is undefined. But we saw an example in 2.7 where, so recall the example from 2.7, which was that the absolute value of x is not differentiable at 0. So when I say not differentiable, that means the derivative does not exist. Okay. So we saw that the derivative did not exist at 0, but clearly we can plug in 0 to this function. If we plug in 0 to the absolute value of x, we just get 0 back out. So the domain of the derivative is possibly smaller than the domain of the function. It has to be at least as small as the domain of the function. It can't be larger, and it could possibly be smaller. So the domain of f prime of x is equal to or smaller than the domain of the function. Okay. So when might the derivative not exist? So there are a couple ways in which this can happen, but basically the idea is that f prime of x is defined via a it's defined via a limit, right? And so if the limit does not exist, then the derivative does not exist. not exist. Or we might say, or is undefined at that point. So I prefer to say if a function value does not exist, I prefer to say the function is undefined there, but really they mean the same thing. If it does not exist, then it's undefined. So this could happen when okay. So we talked about if f of a is not defined, so let me say it this way. If the function is not defined, at the point, and more generally, if the function is not continuous at that point. So actually, here is a fact. If f is differentiable at a point, I probably shouldn't use this terminology yet. So, okay. Okay. If the derivative, okay, let me figure out how to word this. If the derivative exists at a point x equals a, then the function is continuous there. Okay. Okay, so I'm not going to prove this fact, but the proof is actually kind of nice and pretty concise, and but I think it's not that illuminating, so I'm going to omit it. But it is in the textbook if you want to see it. Okay, so that's a useful fact to know. If the derivative exists at a point, then the function has to be continuous there. And then, okay, so that is one way in which the derivative might not exist at a point. Another way, so this is like the example that we saw last time. So the left and right hand limits do not agree. So the left and right hand limits referring to the limit definition of the derivative. So for example, if f of x equals absolute value of x, we saw that the limit as h goes to 0 from the right of f of okay, maybe this is not so clear, but if you go look at the example that oops, here we go. Okay, so from 2.7. Yeah, so that's an example where the left and right hand limits do not agree. I'm not going to write it all out because I think it's more confusing than not writing it out. So, okay. Okay, so we have these, and then we have that if the limit is equal to plus or minus infinity, then we say that the derivative does not exist there. So infinity or minus infinity. Now, so this is a little bit of a, I don't want to say tricky point, but it's something to pay attention to, I guess. The limit can exist and be equal to infinity, right? So we said that it's fine for limits to be equal to infinity. And in fact, we've seen a lot of examples where the limit is equal to plus or minus infinity. But since we have the f prime, so this derivative is a function, we don't want it taking on the values plus or minus infinity, right? We want everything that is an output of our function, we want that to be finite. We want it to be a number. We want the range of the function to be within the real numbers and not include plus or minus infinity. So that's the reason for this particular situation, okay? So whenever the derivative might be equal to plus or minus infinity, then we say it does not exist there. And so we can actually, I think it's good to think about this graphically. So an example of the first type, so situation in which the derivative might not exist would be something like if you have a jump discontinuity like this, so discontinuity at that point A, right? Then maybe it's a little bit more clear to see why the derivative does not exist at that point. So if you were to think of drawing your approximating secant lines and approaching this point A, you can see that they're not going to, if you approach from the left and you're drawing secant lines that are getting closer and closer to A, and then you approach from the right, or sorry, I got them mixed up. So if that was approaching from the right, if you approach from the left as well, then you're not going to get the same, it's not converging to one single tangent line, right? Okay, so that's one example. An example where the left and right hand limits do not agree, it's something that looks like a cusp like this, or a corner like this example that we gave. So this one looks like a corner, and if it's more rounded, then we call this a cusp. And this is an example where the derivative does not exist. So if you have anything pointy or sharp, the derivative does not exist at that point. So you can think of the derivative existing at a point as being, as meaning that the function is smooth there. So it's nice and smooth. And if you were to zoom in really, really far, it would essentially look like a line. So if you were to zoom in on this type of thing, you can see that it would never look like a line. The more you zoom in, the pointier it looks, right? So that's an example where the derivative does not exist. And finally, if the limit is plus or minus infinity, what that means is that we have actually a vertical tangent. So it's hard to draw really well, but so basically that the function gets so steep that the tangent is actually completely vertical. And then in this case, the derivative does not exist at that point too, for the reason that I said before. Okay, and even though I've already been using this terminology, I should write it down. So if the derivative exists, let's see, of f exists at A, we say that f is differentiable at A. Okay? So if the derivative exists, we say it's differentiable. If the derivative does not exist, we say that it's not differentiable. Okay, so we are going to, I think I will do these examples in the next video. So.